Next speaker is Professor Galindo from Imperial College, so please.
Thank you. Thank you, everyone. I'll start also by thanking the organizers for inviting me to be here today, very especially Mike Allen. And what I'm going to talk to you about today is the phase behavior of mixtures in uniaxial particles, especially concentrating on the biaxial phase. So the talk follows very nicely from the one from basic. Yeah, is that better now? Yeah. So the talk follows very nicely from that of Andrew Masters' class before me. Okay, I'll start the talk. With a little bit of background about myself, and just to put you in the picture a little bit of why we're doing the sort of work that we're doing. And I must say that this is work that I was involved in quite a long time ago, almost 7 years ago, and basically my daytime job currently, well, most of the time you can see from my address, is chemical engineering. So I actually work on application on the development of equations of state for what we call complex fluids, but they're not liquid crystals, and the development of theories to look at the phase behavior of these systems. Okay, so that's my usual job, and that's why I have a little bit of background in the beginning, trying to put this work in the context of that work, and kind of motivates why we took the approach we took to study the biaxial nematic phase. So then I will tell you a little bit about mixtures of uniaxial particles. A lot of this background we've seen in previous talks, and really what I'm going to concentrate is on theoretical disagreements. Luckily, there are disagreements between myself and myself, so I don't, upset anyone, okay? So they're good type of disagreements. It's our own, it's taking step by step a theory that evolves and finding different results. So as I said, I will hopefully not upset anyone. Eventually, we turn to computer simulations. I'm a little bit like Andrew Masters in this. I'm not a very good simulator. I do it desperately only when I really, really have to, and usually in collaboration. And eventually, we introduce attractive interactions. I don't think I will get to confine hard-cut spheres. I have that in case I start speaking very fast. But I think what I will do is try to take my time, and I hope you enjoy this bit of the work, and then we can have a discussion on that. Okay, I'm doing this wrong again. So on background, the phase diagram of a simple spherical system is very simple as you see it here, and you all know it. There's solid, liquid, and gas phases only, where we can have positional order. We have positional order in the solid, no positional order in the liquid, and then we have gas phases where there is no cohesion. If we start with this very simple phase diagram for simple spherical particles, and we simply consider now a binary mixture of spherical particles, this very simple phase diagram that I just showed you becomes a much more complex topological space. Okay? In a very nice work in the original paper was the thesis of Van Konijnenberg in 1970 here in the UK, and a review paper came out in 1980. They showed a classification of binary mixtures of isotropic particles. They used the van der Waals equation to do this, to give you an idea. So you just have spheres that can have different sizes. There's a hard core, which is the sphere, and there are attractive dispersion interactions between them. So the parameters that they could modify were the relative sizes of the two components and the relative dispersion of the two components. Okay? And with the simple van der Waals approach, they were able to classify the binary phase behavior of the systems. Okay? And they found that there are 6 types of phase behavior, and classified type 1, 2, 3, 4, 5. Okay? Oh, sorry. These are the phase diagrams projected, so composition doesn't come into these phase diagrams. We have pressure and temperature. 1 and 2 refer to the vapor pressures of component 1 and component 2, and they each finish in a critical point. I should say this is fluid phase behavior. So this, relatively complex topology compared to the diagram I showed you before refers only to the fluids. I haven't even put in the solids, which would make things even more complicated if you go that way. Okay, so even if we only look at vapors and liquids, you go from phase diagrams type 1, where you have simple vapor-liquid transitions, so that's component 1, that's component 2, the critical points, and there's a continuous critical line between the two components as the composition of the mixture changes, basically. Okay, and nothing else very exciting is happening, to very complex systems where you have, for example, let's take type 3, where we have this continuous critical line. So we have a critical line that starts here at the critical point of the less volatile component, and it continues this way, and then it goes upwards to infinite pressures. And I showed you in a different projection in a second what this means, okay? And so all I wanted to discuss at this point is how adding components, so going from pure components into mixtures, immediately adds complexity to phase behavior. And as I said, this is more my usual daytime job, okay? And looking in detail at the phase diagrams, this will be a more usual projection for you. We move from the PT projection to usual temperature composition scale, or if you want pressure composition scale, it would be similar. So we go from type 1 binary mixtures, where we have only vapor liquid coexistence, and this would be the region where we have phase separation, okay? And we would have here the dew line and the bubble curve is how they are called, at some given pressure not very high, so a pressure below both critical points. If we increase the pressure to be above the critical point of one of the components, then again we have vapor liquid separation, but we see one critical point, and this point is simply mapped there. And as you increase the pressure, the critical points recede towards the other component, and you get this continuous line. Okay, sorry. Now, if we have two components that are more dissimilar, for example, they have weaker dispersion interactions between the two of them, this relatively simple phase diagram becomes immediately a little bit more complicated. And in the PT projection, two critical lines appear. So you have a vapor-liquid critical line and a liquid-liquid critical line. Basically, the maximum temperatures at which you can observe liquid-liquid separation. And you can map the spaces like this, okay? On the temperature composition phase diagram, we have the vapor-liquid region, and we have liquid-liquid separation that finishes at another critical point that is usually called an upper critical solution temperature. And you map this point into that one, and you construct these phase diagrams. Incidentally, you can construct these phase diagrams directly by looking at the Gibbs-free energy expression. See if you have analytical equations of state, or say, you know, you don't have to solve it analytically, but you have some form, of the free energy, and you do the second and third derivative of the free energy with composition, and you can solve the critical lines directly. If you increase the dissimilarity of the two components in size and in the ratio of dispersion interactions, the diagrams get even more complicated, where you can have two liquid-liquid critical points, one there and one there. And now you have even more critical lines in the system. There is one that goes like this, there's another one there, and there would be a third one there. And I don't want to over-worry you about this. It's just to, to show you how complex things can get very quickly, okay? And the beauty of the work that Scott and Van Konijnenberg did, in addition to classifying them, they were able to map the complete fluid phase behavior of, let's call them simple mixtures, into a new space that is the molecular parameter space. So they define these parameters psi, theta, and lambda, where you can see the relations of the A of van der Waals of one component or the other component, and the B of van der Waals. So this is the size of the two components. And they were able to map the complete phase diagram of these systems. Okay, and you have regions where you have type 1 phase behavior, type 1 with azeotropes, very important, type 2. And what I wanted you to appreciate is how broad the space is, and how mixtures, for example, of type 4 occur in unbelievably small regions of the phase diagram. Okay? So in the context of what I'm going to talk about now, and some of the talks we've heard, where many of us have been involved in looking for the nematic biaxial phase, we could be facing something like this. I mean, in fact, clearly we are facing something like this, because it's been 40 years where people have been looking for the phase and we cannot find it. When you look at this, my view is that theories should be a better way to approach this than computer simulation or experiment. So if we can map this quickly, if you have an analytical expression that allows you to map this quickly, it should be a better way. And maybe theories can guide experiments. And in fact, the reason we're looking for the nematic biaxial phase is because a theory predicted it. Okay, so on the one hand, I'm a firm believer of theories. On the other hand, as I told you in the beginning, I have disagreements with myself on the theories, because of course now theories have inherent approximations, and sometimes they can be very misleading. Okay? Okay, so moving on now, we leave aside the spherical particles, and of course the reason we're here is because we're interested in liquid crystals. So when a particle is no longer spherical, but it has a non-symmetrical shape, for example, rod-shaped particles, the phase diagram, even for the pure component, becomes much more interesting. And this is a very well-known phase diagram that Shashidhar and Chandrasekhar published in 1975, where you have all these phases, isotropic, nematic, esmetic, and solid phases. And you've seen these representations at the molecular level from computer simulations before. These are for hard spherocylinders of aspect ratio 5, which more or less correspond to the molecule. So the phase diagram for the simple, pure system already much more interesting. And we know also that disc-shaped particles also form liquid crystal phases from isotropic, nematic phases, and columnar phases, and a whole variety of other phases. And the phase diagrams become very nice. And of course, as I said, talking about nematic biaxial phases, Andrew Masters gave a nice overview of this. It was first proposed in 1970 on theoretical grounds, so that's very good. So, and it's a phase positionally disorder with orientational order along two perpendicular axes, and you've seen representations of this before, okay? And we've been looking, many of us have been looking for these phases for a long time because supposedly they should give improved response times, better viewing characteristics, we think, because I find this, I took this from papers. In a way, since we've never, there hasn't been many synthesized, I'm not sure we know that this will be true. So there is the case that maybe one day we make them and maybe they will not be that useful, hopefully not. Anyway, so the search started since the phases were predicted in the 1970s for the stable nematic biaxial phase. And so two approaches have been taken more or less since then. One is where we approach it looking at pure fluids, and this is the very nice talk that we had before from Andrew Masters, for example. So in that sense, I think the two talks fit very nicely. And another approach is where you try to take a mixture of uniaxial particles and see if you can then create a biaxial phase, okay? And there have been recently two very nice reviews, one by Roberto Berardi from the group of Claudio Zanoni, and one from Carlson Chirsky and Dimitris Fotinos on the subject of biaxiality. Very interesting reviews, very nice because you get an idea of the controversies and the issues like Andrew was saying before of do we believe that the biaxial phase has been seen or not. But reviewing very quickly, in the case of pure biaxial fluids, the idea starts thinking that, it follows from theoretical arguments that the more biaxial the molecule is, the more biaxial the phase should be. And also you can think naturally that actually most molecules are biaxial, so we should have a good chance with a pure fluid to obtain a biaxial phase. And there are reports as early as in the 1980s, but there were very quickly doubts saying that the biaxiality had been induced by the surface. Okay, and more recently, in 2004, there was this paper that Andrew showed before, where bent core mesogens, I'll show you the paper, were described as having the nematic biaxial phase. I presented some of this work, I think in 2006, where I thought that was it. I thought they had found it, and found only later that there's a lot of controversy about this molecule. So they provided optical measures of biaxiality. As far as and then, well, there was the later paper of, let me see if I can do this. There was the later paper of Acharya, where they showed supposedly using X-ray diffraction, they agreed with the results that they had found. And if I'm not mistaken, the atomistic, these were atomistic simulations, no, Mark? From Mark Wilson's group, where they didn't see very strong biaxiality, but there was some biaxiality. Is that correct? So at this point, I thought that was it. But if you read recent literature, the review of Dimitris Fotinos is very nice. I think they're not very sure at all about this. You have to be, really on top of experiments. I don't understand them enough to make your own judgment. And I think they were confirmed by NMR. I think everyone agrees that it is NMR data that will confirm that the biaxial is really there. And I think they've been confirmed by NMR. But anyway, where there has definitely, as far as I know, been confirmation of a biaxial phase, apart from the colloidal system that Andrew was showing earlier, is in the tetrapode molecules of Merkel, and where Georg Mell, who works here in the UK, was also involved in this work. Now, of course, you can discuss if these are, strictly speaking, we consider them oligomer particles. So these are more polymeric liquid crystals. And until now, for the bent cores, we were talking more thermotropic, smaller molecules. But anyway, these are oligomers. But I think in this case, there is absolutely no doubt that they have seen the nematic biaxial phase, and it is confirmed by NMR. So this, as far as I know, is more or less where we stand on the search for a pure biaxial fluid that is not polymeric and that is not colored, just simple, a simple chemical molecule that can be monodispersed and where we can see these phases. So still work to be done. Okay. Then the other camp of work, which is the one I was involved in, is searching for biaxial phases in mixtures of uniaxial particles. So the idea is to create a nematic phase where each of the molecules, each being uniaxial, each of the molecules points, is ordered, but points in a different direction, the two directions being normal to each other, okay? And part of the reason for this was that we believed that it's much easier to deal with material design by controlling composition than by controlling the chemistry. Synthetic chemistry is very hard to make new molecules. The people that are involved in it is extremely hard. While once you have two components to control composition, gives you beautiful phase diagrams where all sorts of phases appear, so it should be a lot easier, okay? So this is where this idea came from. Okay, also, such a phase, the idea that two uniaxial particles could lead to a nematic biaxial phase had been predicted theoretically by Alben using a mean field lattice theory, okay? And so, in terms of the theories, what we have to deal with, or what you have in the system, the advantage of adding composition is that we have an added balance of terms in the free energy. So in addition to the traditional balance of orientational versus translational entropy that I'm sure you heard from Professor Frenkel on the first day, unfortunately I couldn't be here, that's the usual understanding of why liquid crystals form, and is the reason why colloidal liquid crystals with no dispersion can form ordered phases. Okay, so to the additional balance of translation and orientation, we have an added entropy of mixing that favors the mixed state always. Okay, so that should help stabilize the nematic biaxial. Okay, so what we did is, we take two simple models, cylinders, one elongated and one disc-like, so a bit like the molecules I have shown you before. The system is fully characterized by the aspect ratios of the two molecules, and we have to follow the directors of the rod and the plate and the angle that they form with respect to the director of the phase and the angle that they form with each other. And we followed, so we took the theoretical approach, okay? And we followed the classic theory of Onsager, where you can write the free energy of the system written like this in a reasonably compact form. I have really reduced notation. Of course, each of these terms, is coming up now, and they are larger. So what do we have here? In the system, we have the usual ideal terms. So actually, this log omega 4 pi, that's just the ideal contribution with the log rho. We have the ideal mixing entropy, the x log x term that you have in simple fluids also. Okay, there is a term related to the orientational entropy. So this term favors disordered states, as you know. And you can see that this term is not particularly density dependent. Okay, so this term dominates in the free energy, if you want, at low densities. Okay, and where f of I is the orientational distribution function. Okay, and then there is a second term which relates to the translational entropy, which is density dependent. And so this term kicks in, let's say, dominates in the free energy at high density, okay? And we can write it in two terms. One term that depends in density, which includes the virial coefficients of hard spheres. We can separate it like this. And a second term where the excluded volumes of the particles are written explicitly, okay? In the Onsager limit, as Andrew Masters was saying before, we work at a second virial coefficient level. So f of rho here is 4 eta. This is simply the excluded volume between two spheres, nothing else. Okay? While in the Parsons and Lee approach, you can include higher order virials by mapping the free energy. This is basically scaling, where you write this density contribution, mapping it to the Carnahan and Starling expression for a system of hard spheres. In effect, taking up to, I think it's 5, 8 virial coefficients. Andrew, you know this better. Anyway, it's how many? Is it 5?
I think it's 5.
I think it's 5. Up to 5 virial coefficients, and it is approximate because it is a mapping. But it actually, using this form of the free energy here, allows you to treat molecules that don't need to be infinitely long. Okay, and I must say the first set of results I'm going to show you, we do work in the Onsager limit in the beginning. I'm just showing you all the equations in the beginning. So these are some of the options you have. In addition to that, the excluded volume terms take this form. So they are functions of composition. Of course, the excluded volume between two rods and a plate is different to the excluded volume between two plates and one rod. So there are functions of composition and functions of the excluded volumes of each of the particles and the orientational distribution functions, F11, F12, and F22. So depending on how the two particles come to see each other, let's say. Okay. So in order to fully describe the free energy, let me see what I have next here. In order to fully describe the free energy of the system, and this is really what we would like to have an analytical expression, even if it has to be solved numerically, but I call this analytical as opposed to a computer simulation, we need to be able to write the excluded volumes of these particles. Okay, and you can see now why we chose the cylinders. Okay, Onsager, in his seminal paper of 49, gave the expressions for the excluded volume expression, which as far as I know, I think is essentially exact, 4 cylinders, okay? And they are written like this. So this would be the one for plate-plate interactions, so flat, short, and fat cylinders, let's call them the plates, rod-rod interactions, and rod-plate interactions, okay? And they are written in slightly reduced units. K1 is the aspect ratio of the plate, L1 over D1, K2 is L2 over D2, and then occasionally we use this small d to refer to the ratio of the two diameters, okay? It's not very important. Really, what I want you to sort of realize at this point is that potentially we know completely the free energy of the system with no huge approximations. I can work at Onsager level second virial, or I can do the Parsons-Lee approach, which would not have huge approximations, okay? However, the problem is that you have probably appreciated that the equations are getting increasingly more complicated. And in addition to that, to look at the phase behavior of the system and to look at the stable states, I need the equilibrium orientational distribution function, not any distribution function. And that, of course, that is done through minimization of the free energy, okay? Usually done with Lagrange multipliers or with minimization with constraints, okay? And eventually, we have to solve a set of coupled integral equations that could end up, that do end up looking something like this, even in reasonably compact notation where the excluded volumes are the ones I showed you before. So it gets very messy very quickly, basically, and this, of course, is usually solved numerically. So this is the point where we have to make some approximations, okay? And this is the point where I have to start, going back. When I was telling you that potentially we can do everything, now we start making approximations. So usually, and most of the work that is out there, we work in the Onsager limit, where we say the particles are infinitely long, well, for starters, we do second virial coefficient only, okay? And secondly, we say the particles will be infinitely long and infinitely flat, so my excluded volumes will reduce to these much simpler expressions, okay? And in addition, the earliest works showing, looking at mixtures of rods and plates, which were by Lekekerker and Struvans, in addition, simplified the sines and cosines with a Legendre expansion up to second order only, because even this, which looks reasonably simple, once you put it into the equations, it's actually, you have to solve it numerically, it's not easy at all. So they used what is, we call the model the L2 model, the Legendre second order, basically. So they use these much simpler expressions for the sine and cosine, such that you end up with essentially analytical equations in the end, okay? And what I'm going to show you now is comparisons of what happens to the phase diagrams when we use this simplification, or if instead of this we say, no, let's use the simple excluded volumes, but I will solve the sines and cosines numerically. I will put the full function. It's numerically complicated, but these days we have the computer power, so we do that. So what happens to the phase diagrams? We start with a system of reasonably short rods and plates. So notice that this is, of course, now approximation number 1. Supposedly, I took the Onsager limit, and now I'm applying aspect ratios that are much smaller, okay? But anyway, so in the L2 approximation, this is essentially the phase diagram that was shown by Lekekerker and Struvans. We have rods on this side of the diagram and plates here, and so we have pressure along the vertical axis, and we have an isotropic to pneumatic transition for pure rods, an isotropic to pneumatic for pure plates. I should tell you that to simplify things, all of the systems I'm going to look, we call them symmetric rod plate systems, in the sense that we choose the aspect ratios such that the excluded volume of the particles are equal. Okay? The space grows even more if you break that assumption, okay? This is why the diagrams look so symmetrical, okay? And this is something we impose just as an initial investigation. So, and when we have this isotropic phase that goes to nematic, and in the middle of the phase diagram, there you have the nematic biaxial phase. In all of the diagrams I'm going to show you, the phase I label, the letter in the middle tells you what is the stable phase. And in dashed, I show you where is a metastable nematic-nematic separation transition, okay? So the nematic-nematic separation is metastable in this model as compared to the nematic biaxial phase, okay? And I think it was partly these calculations that also inspired, and helped us decide, yeah, let's do mixtures because the nematic biaxial phases appear in large areas of the phase diagrams. Okay, what if I do the phase diagram not in the L2 approximation, not the Legendre, second order Legendre expansion? What if I put the sine and cosine in full and I do it numerically? Okay, the phase diagram looks like this. So rods on that size, the pressure scale actually doesn't change much in this case. In some of them it changes quite a lot, but that, to be honest, is not that important. These are, theoretical units. It's not so much of a problem. So isotropic to nematic transition for the rods, isotropic to nematic for the plates. So we see a larger stabilization of the isotropic phase, which we had some stabilization here. This makes complete sense, by the way. As you mix, the entropy of mixing will promote the disorder phase, and this is exactly what you should see, okay? And as the pressure increases, the nematic biaxial is stable, which is very good, and that's the metastable nematic-nematic separation phase, okay? And that's for these aspect ratios. I want to show you, because at this point you might wonder, why do you see a difference? It's kind of trivial, hopefully, but I thought, it's probably useful to see like this. We looked in detail at the Legendre expansion of the sine and the cosine. Until now, certainly, for example, myself, I had never really worried about it too much. I had taken, the original papers. This is what people do, and to be honest, I didn't even think of it. When you think about it, you think, of course, this is an expansion at second order. Is a big approximation, basically. Okay, so this is an error function. This is for the sine and the cosine, an error function that we define as the full. This would be the full, let's say, sine or cosine, compared to the Legendre expanded function. In dash, you have the solution for the L2 case, okay? So there is quite an error, okay? And the lines, you can see many lines, go up to 18th order of the expansion, okay? So there is a big difference. This is why the phase diagrams are different. And you can see that the L2 model, we are making large approximations, and we will see the impact in a second. So if we go to larger particles, interestingly, for larger particles, the same, Onsager theory, L2 approximation. We have rods again here and plates. We see no longer stabilization of the isotropic phase. We see demixing of the two isotropic phases, which is already very interesting. It seems that the particles are getting so large that they really don't want to be mixed even when they are isotropic, okay? You see, in case you're very worried about this, I remind you that you do have cases in simple liquids, as I showed you earlier, where you have separation of spheres if you make the dispersions weak enough. So there's, it's not immediately obvious why, as they get large, this happens, but you can see that it can happen in the systems. And more interestingly, as you go up in pressure, the biaxial phase is no longer stable. So as I told you before, I labeled the stable phases. So these solid lines represent the nematic-nematic separation. So there's a nematic reaching rods, phase separated with a nematic reaching plates. And in between, this is all metastable, okay? And the dashed line indicates where the metastable phase for the biaxial would be, okay? But its free energy is higher than for the phase separated system, okay? If I do the same, if I look at the same system, but now apply the numerical solution, so the more correct solution, the biaxial phase is stable. Same system, but now doing it fully numerically. The isotropic separation is still there, but this is very important. So we have the nematics, the biaxial nematic stable. Okay, so what have we done so far? We have, for small aspect ratios, the L2 approximation and the full numerical solution seem to agree, and they both lead to stable nematic biaxial phases. Okay, for large aspect ratios, however, we find that the numerical solution predicts stable nematic, stable biaxial nematic phase. Okay, and then maybe this is the point to say, okay, what do the experiments suggest? Is there anything out there for mixtures that might help? So, and what we know is that colloidal systems, which we have in the next slide, colloidal systems, they're shorter, but colloidal systems which were looked at by the group of Hengleke-Kerker in Utrecht lead to very clear nematic-nematic separation. Okay, so these are rod-like and plate-like molecules. Mix them together, and there you have the nematic-nematic separation. So they don't observe biaxiality. And yes, admittedly, they're much shorter than the ones I was showing you before, but still, I think they've looked at quite a few systems. We published a paper in 2003 with David Dunmore, who at the time was in Southampton University. They were the experimentalists. I didn't do any of the experiments. But what they observed, this was a paper where we presented experiments combined with simulations that we were doing at the time, and I will show you later. And what we observed was a stabilization of the isotropic phase and phase separation. So very much in line. I guess, again, the systems are the short ones. Again, impossible to find the nematic biaxial in the mixtures. Okay, I think that's the main message I want to pass you. So at this point, I'm trying to understand which of the two theories was the correct one. And are the experiment, is the theory really that suggests that there is no nematic biaxial correct? We turn to computer simulation, because I show you here the experiments are for short systems. Okay, and I remind you that both the L2 model and the numerical model suggested a stable biaxial nematic. Okay, so we turn to computer simulations, and this, as I said before, I definitely, simulations are, I'm definitely not an expert, so they're reasonably basic, but just enough to at least tell us what we're looking for. Okay, so we did MVT, very straightforward simulations with 510 hard spherocylinders, 510 cat spheres with aspect ratios chosen such that the volumes of the particles were the same. And notice this, we chose particles of the same volume, not the same excluded volume, which is strictly speaking, I think it's a mistake. But anyway, this is what we chose at the time. I think retrospectively we should have done obviously same excluded volume, but it's not important for the final conclusions. And I remind you, the reason we chose them also, especially the 5 aspect ratio cylinder, they had been studied, in a lot of detail. So we knew very well the phase diagrams of the two sides of the two pures. And the main thing to know is that the isotropic nematic transition for the rods occurs at 41% packing fraction, and for the plates at between 41 and 44. This one is much stronger first order. Okay, we choose particles of equal volume, and we study mixtures of 50-50. So we start with a total composition half and half, and just compress or increase the density, I should say, because they're MVT, and see what happens in the system. Okay, the simulations are were unbelievably long. For these days, they don't look very long, but I tell you, this was this was a lot of patience and time, and of course we follow the nematic and biaxial order parameters as we go along. Okay, and so what did we see? We saw for a packing fraction of 0.44, where both pure components would have had the transition for isotropic to nematic by now, we see nothing. And this was run for, I think this was run for 10 to the 9 moves. It was there, slowly. If it was a good year of simulation, very slowly, just patiently while we were doing other things. And I am convinced there's nothing there. Okay, and the phase it confirms the stabilization of the isotropic, which is what I think it makes a lot of sense from the free energy point of view. If we increase the density enough, we find phase separation. So this is very nice, a spontaneous phase separation of the two systems. This took forever, of course, because these are hard systems, and the surface tension between the two phases is, we haven't calculated, but it must be unbelievably small. So the force to separate the two is very small, so it just took a long time. But it separated spontaneously. This is a small system. We did larger ones afterwards, and it definitely phase separates. So we confirm. So unfortunately, no nematic biaxial, but confirmation of two ordered phases in coexistence. And you can see the systems are small, so we can't really say very much about the detail of the densities, but we can say a bit. We went as far as to draw a tentative phase diagram, knowing that the error bars are large, but the phase diagram would look something like this, where this is in density, but there's stabilization of the nematic phase, clear separation of two ordered phases, nematic and columnar. And we saw some smectics up here. And I just remind you, this is the paper where we put everything together, that this was the experimental phase diagram. The experimental phase diagram looks upside down because it's a temperature scale, okay? But it's essentially the same, okay? So we were happy with the work, other than no nematic biaxial phase. So where are we at the moment? So the simulations confirm that the disordered isotropic state is favored on mixing, and that we find two ordered coexisting phases, but no nematic biaxial phase. Okay, and this is what I meant when I said theoretical disagreements. Okay, so we have two models. One suggests nematic separation, the other one doesn't. We look at experiments, we can't see anything, and basically we went back to the theory. Okay, so let's review the approximations that we made. Okay, so we revisit the theoretical approach, and now what we do, we noticed, if you remember, in the excluded volume terms, because they were very complex, we assumed very long particles and took only the leading terms of the excluded volumes. Okay, so we go back to that. These were the expressions. When the aspect ratios become very large, the leading terms are essentially the ones at the end. So there were this one, and just that one. I can't remember if I have them highlighted. No, okay, so they're just those. Now, instead of that, we keep the full expressions. This gets very messy, but numerically savvy Varga, who's really the one that did the work, okay? Very, very good theoretician, extremely good at numerical methods, and he was the one that solved this. So you put it all in the computer, you solved it numerically. So I remind you, you put that excluded volume now in full into the same expression of the free energy. I will show you now results, and since we were going through the pain of putting the full excluded volume, we decided to go to town with this in full and to put the Parsons-Lee free energy for the hardest, for this mapped hardest sphere one. Because once you're going to go through the pain, you might as well, do it with this one and not have the worry, is it the second virial coefficient that is giving me different results, okay? So we use the Parsons-Lee, so the Carnahan-Starling up to 5 virial coefficients of the hardest sphere and the full excluded volume here, and solve numerically, of course, okay. So I remind you, for the L over D system, we had stable nematic phase in the Onsager limit, and if we now do the Parsons-Lee theory with end effects, so the complete excluded volume, the nematic phase becomes metastable. So we don't see the nematic biaxial phase. We have nematic separation, okay, for the short particles, and exactly the same thing for the long particles. So no nematic separation. Sorry, no biaxial phase. Okay, so we see only nematic separation in both of them. Okay, so aside from the message of the fact that, well, I think, let me finish this and then I'll give you the other message. So what we have done is really highlighted this very delicate competition of the terms of the free energy, okay? And we have ruled out, okay, the possibility of having uniaxial and biaxial nematic, we have ruled out uniaxial to biaxial nematic transitions in mixtures of uniaxial particles. I think this statement might be a bit harsh because we've only looked at particles with equal excluded volume, okay? So I think you have to take that with a pinch of salt, or maybe I should just have 4 equal excluded volume systems, okay? Together with this message, especially the first part, and in reference to the theory, I wonder if, for example, the work of bent core mesogens, as I read through the papers for the experiments of the bent cores, where there was a lot of criticism for the molecule that was synthesized because the angle was 140 instead of 110, I think, you have to be careful, because depending on the approximations of the theory, this 110 or 19 that they think is the optimal one, I think it might not be, basically. I think you have to take theories with a pinch of salt. You can see the wealth of results that you can have. So when you're using the Onsager limit and you're trying to use it for a real molecule, to me, 110 angle or 140, maybe it's not such a huge difference. Anyway, this is, small controversy there. Okay, so basically, at this point, does it mean that it's not possible to stabilize a biaxial nematic phase when we mix 2 uniaxial particles, okay? And I'm almost finishing. There's this nice work by the group of Georg Mell, where they took 2 particles, one looking disc-like and one looking a little bit more rod-like, which is in fact this side here, and they did 2 things. They forced them to be together through this entity in the middle, and they add, let's call it S surfactant in the middle, okay? And what they find is full miscibility of the nematic phase. So essentially they conclude it is possible, of course, to mix 2 particles that are uniaxial and stabilize them in a fully mixed phase. Okay, so with that in mind, we went back to our models and realized, as Claudio Sanroni has been asking about this in many of the talks, we need dispersions, okay? And of course, the people that work with the Gay-Bern have acknowledged this for a long time. So we just wondered if by, let's say, brute force, if we put dispersion into our models, we can stabilize a nematic biaxial phase. If we do, and these are simulation results, if we do, it gives us a reason to go back to the drawing board and do the hard work of developing theories with dispersion, and that is very, very hard work. Okay, so you need a good reason to embark on that for anisotropic particles. Okay, so we propose two models: a model where we have where we have uniaxial rods and plates with isotropic dispersive interactions. So just a simple square well around each of the particles. Okay, and you have here the dispersion. So the interaction is infinite if, of course, the particles touch in whichever orientation they're approaching each other. There is a negative energy for a given range, okay, from some closest distance dm to some arbitrary parameter, okay, reasonably long to encompass, a few particles around them, okay. So we compare this model, we use this one, and we also proposed, and this is the work of Alejandro Cuetos, really, who then went on to do a postdoc with Marjolin. So he suggested this other potential, okay, a potential that is anisotropic, which promotes this sort of conformation. Okay, after starting the simulations with the isotropic dispersion, it was clear that we were not going to go anywhere. I'll show you in a second. And so he said, why not force them to be in this conformation? Okay. So for the case of the isotropic interaction, the isotropic dispersion, amongst many other phases, the nicest one, the most interesting was this smectic biaxial phase, which apparently is called a Macmillan phase. Okay, we follow this order parameter, which tells us that the phase is biaxial 0.5. The phase, is very beautiful. You can see it's layered. Okay, and it's biaxial. If you calculate the order parameter, the director of the plates is pointing mostly on average. I think on average is mostly pointing that way. Okay. And the director of the rods is pointing upwards like this. Okay, so it is biaxial, but it's very clearly smectic. And as someone mentioned before, the fight for the stable biaxial phase is not that biaxial phase don't exist. Of course they exist. It's having them, but not allowing the system to solidify or form a smectic. Okay, so for this system we didn't find it. We calculated the geofars. Okay, so these are the geofars projected along the director. So that's one of them, and that's the other. So along. I can't remember which is which, there with reference to the layer, but basically, yes, you see that in the layer the system is disordered, and along the layer the system is ordered. So these are the layers. Okay, so it's a smectic phase very clearly. Then, luckily, for the isotropic case, for a particular value of energy and at a particular temperature, of course, okay, and we go back to the very broad space of parameters, we managed to stabilize, or rather Alejandro managed to stabilize this phase, which is definitely a biaxial nematic phase. There is no positional order. The B2 parameter of biaxiality is very high, okay? And although you see slight layering, depending on how you look, we looked at the geofars and there is definitely nothing there, okay? This is the general geofar. It's of rods, plates, and the crossed one. I can't remember which is which exactly, but this is the important one. These are the ones projected along the principal directors, and there is no order. There's small, very local order, okay? But on the whole, the phase is a nematic biaxial. Okay, so in summary, I have shown you that there's a very subtle entropic and energetic balance, of course, in these mixtures, okay? And especially when you deal with mixtures, okay? That rod plate mixtures, if they have hard interactions, as far as we can see, they just want to phase separate, which makes a lot of sense, I guess, okay? We have managed to stabilize nematic biaxial phases when we add attractive interactions, basically, okay? And I will leave it here. Yeah, let me go, actually, no, let me have here, so this is my exit point. And I have to acknowledge, okay, all the people that did the hard work. Alejandro Cuetos, who's he's an excellent simulator. David Dunmore, who did the experiments. Andrew Haslam and George Jackson, who many of you know, and we've collaborated, as you know, for many years together. Andrew Parry helped in some of the work, Dimitris Fotinos, and Alekos Vanakaras. I was lucky to spend time in Patras with them. Manuel Piñeiro, and Savi Varga, who really is the theoretician that took charge of the work. Thank you.
Thank you very much for your talk. So we do have time for a couple of questions.
I'm free to go.
yeah, maybe people are tired of long discussions and lunch is ahead. So, okay, let us finish with this and let us thank the speaker again.